Hello and welcome to this lecture. We have seen orthogonality, orthonormality and the notion of an orthonormal basis and how there are various different interesting orthonormal bases in CN in particular, right. We had the Fourier basis, Hadamard basis and all that. Now, what is so great about orthonormal basis? So, here is one amazing property, very simple property of orthonormal basis. Supposing I give you a basis of Fn, V1 to Vn, general basis may not be orthonormal. And then you have a11, an1, a1n, ann, etc. Coordinates of v1 is that, coordinates of vn is that. Now, if I give you another vector v which has coordinates b1 to bn and then ask what are the coordinates of this v with respect to this new basis. Okay, remember I am originally thinking of the canonical basis as the basic truth here. So, all of these are with respect to canonical basis. Now, I have a new basis here v1 to vn. And I want coordinates of v which is b1 to bn in terms of this basis. If that is the question I am asking, I have to solve a system of linear equations. We have seen this before, right. So, this basis vectors have to be put into columns, the coordinates have to be put into columns, and then that matrix times my x1 to xn has to be b1 to bn. Once I solve this, my coordinates of v will be x1 to xn. The coordinates of v in this basis are x1 to xn, right. So, you see x1 times the first column plus x2 times the second column, so on till xn times the last column is equal to b1 to bn. Okay. So, this will always have a solution because these are linearly independent and this will have a unique solution. This will be an invertible matrix, you will get the answer. Okay. So, you have to solve a system of equations to find coordinates. But let us say now v1 to vn is an orthonormal basis of Fn. Okay. Then the coordinates of v are simply given by Euclidean inner products. You take v and take its inner product with v1. That is the coordinates of v with respect to v1 to vn. And then second coordinate is v comma v2, inner product v comma v2. The last coordinate is v comma vn. That is it. You do not need to do any equation solving. If you have an orthonormal basis, you simply take a dot product with the basis vectors, you are done. Okay. So, that is an amazing way to justify or promote the use of orthonormal basis, and that is why orthonormal bases are very popular. So, here is a proof. The proof is very trivial. We have seen this before. V is x1 v1 plus xn vn. You simply take inner products with both sides on vi and you see only xi remains, everything else goes off to 0 because of the orthonormality. Okay. So, orthonormality plays very well with linear combinations because of this property. Okay. So, this is one of the reasons why this finding coordinates with respect to orthonormal basis is very easy. So, here is a problem which you can try. If I give you a vector 1, 2, 3, 4 and I want coordinates with respect to the Hadamard basis or the Fourier basis, all I need to do is dot product. But when you do dot product with complex vectors, remember the conjugate. Okay, do not forget the conjugate when you do dot product for complex vectors, but it will work out. So, you will get quickly coordinates very easily just using the orthonormality. Okay. So, that is one idea which is very useful. Okay. The next thing is, see I gave you these magic bases, right, this Hadamard basis and Fourier basis. What if I do not have such magic, right? So, what if a lot of these things are not known? Supposing I only have a set of linearly independent vectors. Is there a way I can go towards orthonormalization without changing their span? Okay. So, I have v1 to vk, right? These are a set of linearly independent vectors. They span some space v1 to vk, let us say. Linearly independent, not independent, it is okay. So, this is a set of vectors which they span. Can I find an orthonormal basis for this span of v1 to vk starting with v1 to vk? Is there a process by which I can do that? In other words, the question I am asking is does every subspace have an orthonormal basis? Is it true that I can find an orthonormal basis for any subspace? Turns out the answer is yes, and that answer is Gramm-schmidt orthonormalization. You can start from an input set of vectors and go towards an orthonormal set of vectors with the same span. Okay. So, that is very useful. Let us see how that is done. Okay. So, you remember the previous thing we saw was the elimination process. In the elimination process, we did not go to a set of orthonormal vectors, but we went to a row reduced form which was useful in solving equations. But that did not need any inner product notion. Now that we have inner product, we can do more. We can do orthonormal work. Okay. So, the first thing we do is start with v1. They are linearly independent, we will assume of course they are non-zero. So, you can divide by norm of v1, I normalize v1. Okay. So, my orthonormality I need 2, right, I need normal, each vector should be normalized and the dot product should go to 0. Orthogonality also is important. So, you can take u1 is v1 by norm v1. That is the first vector that I am taking. Okay. Then I will do a loop. Loop variable is j goes from 2, 3, so on till k. So, every vector I will consider here. For every j, let us say j equals 2, okay, just for j equals 2 and then 3, etc. For every j, I am going to make a vector wj. What is my wj? I will take vj and then I will subtract from it the part of vj that is along uj minus 1, okay. So, I take a dot product of vj with, not dot product, the inner product of vj with uj minus 1 and then I multiply with uj minus 1. So, if you remember, the part of a vector which lies along another vector is the inner product multiplying that vector. Of course, you divide by the norm for something, but even if you do not divide, this lies along uj minus 1. So, you have vj comma inner product uj minus 1 multiplied by uj minus 1. And then likewise, I subtract every other ui before it, okay. So, if you do that, you will get this form, okay. So, maybe I will take a little bit of time and show you what happens for j equals 2 and all that, okay. So, we start with v1 to vk. I started with u1 being v1 by norm v1. What do I do for w2? W2 is v2 minus inner product of v2 with u1, right. So, j is 2, inner product of v2 with u1 times u1, okay. So, what have I done here? I have taken v2, I have subtracted the part of u1 that lies along the part of v2 that lies along u1 and I have left an orthogonal part. Have I left an orthogonal part? You can check that, right? See what happens if you do inner product w2 u1, okay. So, notice what happens here, you will get v2 u1, right, minus this is a scalar, right, which will come out v2 u1 inner product u1 u1. Do you see that? When I take an inner product on both sides with u1, I have w2 u1 on the left hand side, I have v2 minus this is a scalar, right. So, think of this as some c, okay. So, v2 comma u1 minus c times u1 comma u1. What is u1 comma u1? It is just 1. So, v2 comma u1 minus v2 comma u1 goes off to 0. Do you see that? I hope you see that, okay. So, this w2 which I have formed in v2 minus this guy is actually, this implies w2 is perpendicular to u1, okay. So, what I have generated here is u1 comma w2, okay, right. w2 is v2 minus this into u1, right. So, this is like an elimination step. So, span of u1 w2 is the same as span of v1 v2, okay. I hope you see that. See, u1 is nothing but u1 v1 by norm v1, right, and then we are doing v2 minus something into v1. So, the span remains the same. If anything that you write as v1 v2 combo, I can write as u1 w2 combo and the other way around. It is the same proof as the elimination, okay. So, it is like an elimination step, except the constant we are using is not to make one particular entry 0, it is to make the inner product 0. So, we pick the constants to be the inner products of in suitable way v2 comma u1. I hope you see it. There is a lot of elimination mirroring here, except you pick the constants differently, the row manipulation that you do differently. If you want, you can write it like that also, right. So, you can write it like that. So, we have v1, v2, vk here. The first thing you do here is v1 by norm v1, okay. The second is v2 minus u1 is like this, and then you make a w2 which is v2 minus v1 u1 times u1, okay. And then you see here that this is the span won't change, span remains the same, right. Span of u1 w2 is same as span of u1 v1 v2, okay. Now, this is not normalized. So, all you have to do is to normalize it. I will let my u2 be w2 by norm w2, okay. So, I have a u1 u2 here, span of u1 u2 is the same as span of v1 v2, but interestingly u1 is perpendicular to u2. Okay. So, I achieved that. Now, the same thing is achieved when you carry on further and further. So, notice what happens here. So, if you go to W3, now W3 is going to be V3 minus V3 comma U1 U1 minus V3 comma U2 U2. Is that okay? So, now notice what happens here. See, U1 and U2 are already orthogonal, right? So, if I do W3 comma U1, you will get V3 comma U1 minus this alone will survive, right? V3 comma U1 times U1 comma U1, that is 1, and then U2 comma U1 will go off to 0, so this goes to 0. So, likewise W3 comma U2 is also 0, right? V3 comma U2, this will go off to 0, this alone will survive, V3 comma U2 will go to 0. So, when I do this step here, I take the part of V3 that is along U1, subtract it off, part that V3 that is along U2, subtract it off in such a manner that what remains is perpendicular to all that I subtracted off. Okay. So, that is the crucial part. So, W3 when I form like this, I have this wonderful property that W3 is perpendicular to U1, W3 is perpendicular to U2. So, all I need to do is to define U3, normalize W3. So, when I normalize W3, I get my wonderful result that span of U1, U2, U3 is the same as span of V1, V2, V3, right. It is exactly like an elimination step, no? It is a row operation that we are doing in this sense. V1, V2, V3 and U1, U2, U3 are orthonormal. Okay. So, this is the process that is formalized here. Okay. So, for every j, I make a Wj which is Vj minus the part of Vj that is along Uj minus like that, part of all the Vj's that are in previous Uj's subtracted in such a way with this inner product, so that what remains is orthogonal to each of these guys, and those guys are also orthonormal to each other, and that works out. And then I take my normalization, I take this Wj and normalize it, I get my Uj. Okay. So, the claim finally is U1 to Uk is a set of orthonormal vectors, very easy to see that, and more interestingly, for every j, span of U1 to Uj is the same as span of V1 to Vj. It is not just only at the final step the spans are the same, in every intermediate step also the span is the same. So, this is also very useful, it will come out to be very useful later on. Okay. So, I hope this result is clear to you. So, now this clearly shows you, if you give me any set of linearly independent vectors or any vectors actually, right, even if they are not linearly independent, somehow in the row operation they will go off to 0 and the dimension will reduce. So, you have a way of going from a spanning set to an orthonormal set with the same span. Okay. So, every subspace now has an orthonormal basis, and there is like a mechanical procedure called the Gramm-schmidt orthonormalization procedure that you can use to run it. Okay. So, it's very useful. So, you should get some experience with Gramm-schmidt. Today, a lot of computing packages will do these for you, but nevertheless, just to get a sense of how this works for small questions, and these are the questions we can ask you in quizzes and all that. So, you should get practice with eliminating to get an orthonormal basis. That is the Gramm-schmidt operation of normalization. Okay. So, once again, when you do complex, watch out for the conjugate. Okay. So, that is the Gramm-schmidt orthonormalization. Thank you very much.